This video is on nuclear binding energy and mass defect. Question number 1, define isotope. Isotopes are two different atoms with the same number of protons in the nucleus but different number of neutrons in the nucleus. Question number 2, isotopes have the same chemical properties but different physical properties. Question 3, define mass defects. Units. Mass defect is a difference in mass between the individual parts of the nucleus and the whole nucleus. So let's take a look at this equation. Mass defect is the number of protons I just highlighted plus the number of neutrons. It's the mass of all the protons plus the mass of all the neutrons individually minus the mass of the nucleus. And this is greater than 0 kilograms. Okay, once again, mass defect, it's the total mass of the individual protons plus the total mass of the individual neutrons in the nucleus minus the mass of the nucleus, which is greater than 0 kilograms. So conclusion. The mass of the nucleus is less than its individual parts. The mass of the nucleus is less than adding up all the masses of the individual neutrons and individual protons in it. Think of how crazy and non-intuitive this is. So once they're all in the nucleus, their mass is actually less than what they are individually. The protons and the neutrons. Question 4. Which has more mass, 2 individual protons or 2 protons in the same nucleus? 2 individual protons have more mass than 2 protons in the same nucleus. So once again, think about how crazy and non-intuitive this is. Question 5. Define binding energy. What are the units? Binding energy is the energy required to separate all the nucleons from the nucleus. Okay? So binding energy is delta M times C squared, which has units of joules or mega electron volts. The higher the binding energy per nucleon, the more stable the nucleus. Question 6. Draw and label the binding energy curve. Label the horizontal and vertical axis. Label the most stable element. So here, the vertical axis is binding energy per nucleon, average binding energy per nucleon. Then the horizontal axis is number of nucleons in the nucleus. So you see hydrogen, which only has 1 proton in it, its binding energy per nucleon is 0. Then it goes up to hydrogen 2, helium 3, hydrogen 3, helium 4, then it goes down to lithium. Then you could see the most stable element is iron. Fe is iron 56. 56 protons in the nucleus. Then it goes down. So anything to the right of iron, we have fission reactions. Anything left of iron, we have fission reactions to make it more stable. And anything to the right of iron, it goes to the left. We have fusion to be more stable towards iron. Question 7. Define atomic mass units. Atomic mass unit is 1/12 the mass of a neutral carbon-12 atom. 6 protons, 6 neutrons, 6 electrons. So 1 atomic mass unit is about 1.66 times 10 to the minus 27 kilograms. Question 8. Use the equation delta E equals delta MC squared to find the energy equivalent of 1 atomic mass units in joules and MEV over C squared. Okay. So one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. So fix this. This should be 10 to the minus 27 kilograms. So you see here, I did not approximate one atomic mass unit and the speed of light. So E equals mc squared, and I end up getting this number here. Now let's convert these joules to electron volts. This fraction here is equal to the number 1. This is the electron volts. Now let's convert this electron volts to mega electron volts, which is this, 931.5 MeV. So 1 atomic mass unit times c squared is 931.5 MeV. And we can use this to convert mass to energy. Because remember, E equals mc squared. E is energy. Mc squared, the m is mass. Question 9. Determine the binding energy per nucleon for a neutral carbon nucleus. So 1 atomic mass unit is 931.5 MeV over c squared. The mass of a neutral carbon nucleus, it's going to be the mass of 12 protons and, the 6 protons, 6 neutrons, and 6 electrons, minus the 6 electrons. What I've highlighted here are the 6 electrons mass. So this is the mass of the carbon nucleus in yellow. Now the mass of 6 individual neutrons and 6 individual protons is here. Okay? So now I'm going to subtract the green and the yellow. The green and the yellow, when you subtract the two, you get the mass defect, which is this. So the mass defect times 931.5 MeV over c squared is what I've highlighted in purple. And this divided by 12 nucleons is this. So this is the average binding energy per nucleon for carbon. Okay. Question 10. Define transmutation. Transmutation is the conversion of one chemical element or an isotope into another. Question 11. Determine the number of protons, neutrons, and electrons that make up chlorine. 37. So just by looking at this, we know that there's 17 protons, therefore there's 17 electrons because it's neutral, and we got 37 minus 17, we get 17 neutrons. Determine the total mass of a chlorine-37 nucleus based on the sum of its separate parts in kilograms and atomic mass units. So individually, 17 protons and 20 neutrons have this mass here. I just highlighted it. 6.19141 times 10 to the minus 26 kilograms. And this is its mass in atomic mass units. Part C, the atomic mass of chlorine-37 is approximately 36.965903 AMU. So what I just highlighted here is the mass of the nucleus of the individual protons and neutrons. This, what I highlighted, is the mass of the nucleus when the protons and neutrons are together. So what I've highlighted here is the mass of chlorine-37 minus the 17 electrons. So now what I've highlighted is just the mass of the chlorine nucleus. And this 6.13894 is here. This 6.1941 is the mass of a single chlorine 37. So this is our solution. So I'm just thinking, where did I get this 6.1941? I got it here. Okay. So this is the total mass of the individual neutrons and protons right here. This is the total mass of the individual neutrons and protons, what I've highlighted. This, what I've highlighted, is the mass of the chlorine nucleus. And this is the mass defect. And this is the mass defect in terms of MeV. And this is the binding energy per nucleon for chlorine. Question 12. What happens in nuclear decay if the mass difference is positive? Is nuclear decay possible? If the mass difference is positive, then the reaction releases energy. That means it's exothermic. The decay is spontaneous and releases energy. So yes, nuclear decay is possible. If you go on this OpenStax link, you're going to see an example of mass difference being positive. Okay, so this mass difference is positive. I've highlighted it in this red box. And let's read this together. This decay is spontaneous and releases energy because the products have less mass in the parent nucleus. Question 13. What happens in nuclear decay if the mass difference is negative? Is nuclear decay possible? If mass difference is negative, then the reaction is endothermic and must be induced with an energy input. So you must add energy to the system. So, question 14. Describe the strong nuclear force. It's an attractive force that exists between all nucleons. It's the strongest of all forces at short ranges, and the force dissipates to zero at about 10 to the minus 15 meters.